Welcome to this 17th lecture video for Physics 4C. Finally introducing quantum mechanics this semester. Unlike special relativity, where we could essentially start with the two postulates of special relativity disconnected from all historical context, we need a gentler, more gradual introduction to quantum mechanics. So this week, we will start with the discussion of the blackbody radiation being considered at the turn of the 20th century, and the theoretical difficulty, that is the ultraviolet catastrophe, it was causing for the physicists at the time. Through what can only be described as an ad hoc assumption, Max Planck developed the first successful model of the blackbody radiation. Then Einstein took Planck's unjustified assumption of energy quantized by h, now called Planck's constant, times frequency even one step farther to apply it to the light, introducing the idea of photon, a particle of light, in order to successfully explain the photoelectric effect, which was yet another phenomenon that the classical theory of electrodynamics had trouble explaining successfully at the turn of the 20th century. Having introduced the photon idea, and already having covered relativistic mechanics last week, we will derive the Compton Scattering formula, describing a collision between a high-energy photon and a charged particle initially at rest. It was Richard Feynman who said, "I think I can safely say that nobody really understands quantum mechanics." As we start quantum mechanics, I want you to feel comfortable thinking and feeling that the new assumptions and ideas we introduce do not really make sense. Next week, we will look at the semi-classical models built by mixing these quantum assumptions with still essentially classical analysis of a setup. All right, does everyone here remember how to use diffraction grating? So before I turn off the light, this is how you should be holding it, horizontal wise. Put it right in front of your eye, and I'm going to ask you to look at that after I turn off all the other sources of light in the room. Maybe I should actually just turn this off. Yeah. So this is an example of what's called blackbody radiation. And what's easy to miss when you are looking at blackbody radiation just on its own is that it looks red. It's easy to think red is the only color there. That's why you have the diffraction grating. Look at it with the grating and see if you can locate the diffracted light. So, as you look at it straight, you shouldn't see anything strange. But look maybe about, 30, 40 degrees to your right, you should actually see a flame that's kind of in the middle of a spread out thing. Do you see that? And do you see the spread of all the colors? Like, do you see green or blue color in there? You definitely see green, right? Okay, now let me do this. I'm going to turn off the flame so that all you see is the glow of the stainless steel. But, it's going to cool down pretty quickly. I wanted everyone to be ready when I turn off the flame. Everyone ready? Okay. Let me turn off the flame. So that's a blackbody radiation. No flame, just a very hot object emitting light on its own. And as you look at, okay, I don't see blue anymore. Do you see green? Yeah. Yeah, you see green and yellow, right? So what you're looking at, that's a blackbody spectrum. And how many here, anyone still looking at it? Everyone had a chance to look at the blackbody spectrum? So the different colors? Okay, good. So how many here remember seeing an object
that glows because, oh, sorry, were you still looking at it? How many here remember looking at an object that was glowing because it was hot? Like, it was that, that's not the only time you've seen that, right? Where else have you seen that? Stove? Yeah, electric stove. So blackbody radiation is a quite common phenomenon. You see it all the time. I do this as a demo as if it's something that's rare. It's not. And so I think we treat this very briefly. An object that is hot emits radiation. When we do thermodynamics in physics 4b, we talk about 3 different ways of transferring heat. There's conduction, convection, and the final one is radiation. And I know in my class we don't quite spend a lot of time on radiation. In case there are other instructors who do it differently. Do people remember what you know about, well, what do you know about radiation? Like what factoids have you been told in physics 4b that you still remember?
There is a T4 equation.
There's a T4 equation. So when you, yeah. So this is what you might know about something called blackbody radiation already. If not, that's fine. So you have this expression that somehow the rate of power transfer, so I guess a rate of heat transfer was proportional to T4, T to the 4th power. And it's actually called, there's a name for it. I like to give names because that's how you search for things. If you want to search it, it's hard to search for T to the 4. But if I tell you that there's something called Stefan, am I spelling Stefan right? I may be spelling Stefan wrong. Stefan Boltzmann law, which says that intensity of blackbody radiation, so intensity of blackbody, and you remember how intensity was defined, power per area, is given by sigma. This is the Stefan Boltzmann constant. Well, just look it up. Sigma times T to the 4th power. So this is something that, you depending on your instructor, they may have covered it, they may not have. I know I don't cover it because you don't really do anything with it. But I want you to bring your attention to this now because I'm trying to introduce how we stumbled upon a set of laws of physics that we call quantum mechanics. And quantum mechanics has a bit of a traumatic childhood beginning that quite different from special relativity. With the special relativity, I gave you some experimental basis of special relativity, Michelson-Morley experiment, but I hope everyone remembers me saying this. I told you that that experiment didn't affect Einstein at all. Einstein was a theorist. He came up with the special relativity kind of theoretically. This was the set of rules that made sense in the world where Maxwell's equations were correct. Quantum mechanics is completely the other way. Quantum mechanics is it finds its origins in experiments. It's specifically experiments that contradicted theoretical predictions. So what you just saw, blackbody radiation, that's one of such experiments that, I guess you could put it this way, that defied theoretical explanation in an attempt to come up with a theory to describe what people saw quite plainly, what they could see experimentally. That's where people discovered quantum mechanics, really piece by piece. And what I'm hoping to introduce today that we kind of need for Thursday's lab is the quantum mechanical nature of light. So let me put this on the proper place where, so you saw the blackbody spectrum, right? You have some sense that the blackbody spectrum, it's a range of colors. Let me actually show you a blackbody spectrum. Actually, let me do it this way. Rather than, your textbook has one. But PHET simulation actually has one that's better, where I can actually change the parameters. So how hot do you think that sphere was? So, take a guess. 1,000 degrees C? Sounds reasonable. People with the physics 4B here, do you remember your physics 4B red hot calorimetry result? Okay, is it at least between 1,000 and 2,000 degrees C? All right, so no more than 2,000 degrees C. All right, so let me use this. This is a simulation that just show you what blackbody spectrum looks like based on the temperature. So if it's 1,000 degrees C, then let's say the temperature might be something around, I don't know, 2,000 Kelvin. So it's actually quite a bit high. Oops, I need to zoom in. All right, so this is what this says the spectrum was. Does that look like the spectrum that you remember seeing? So what you remember seeing is reddish color, right? So, so this is what I was saying, that what you are seeing is not exactly the spectrum. What you are seeing is a kind of a product or convolution of your eye's response function, what your eye can see, and what that emits as light. What that emits as light is actually mostly in infrared. In fact, even if you were to get this as, so this is a little bit higher than oven temperature, which also glows. Even if you got it as hot as light bulb, actually the maximum of intensity will still be outside of visible range. That's why light bulbs are so inefficient and LED lights are so much more efficient. But what you do see here is this feature. So, I mean, you did see red and green color. And if you zoom in enough to the spectrum, you can see, yeah, I saw red here, and I saw green here. And I looked for blue, but I couldn't quite see blue because there was very little blue there. So that's the spectrum you saw. So that's the blackbody spectrum, and people could make this measurement, and I guess they probably had difficulty measuring infrared. But what they did know was when you have a hot object that's glowing, as the object gets hotter, as hot as light bulb, the spectrum shifts to shorter and shorter wavelength. In fact, I don't know if Wien's displacement law. Yeah, we definitely don't cover that in 4B. So there's a law that describes something called the Wien's displacement law that says the product of the wavelength and the temperature is somehow constant. So people have been studying this blackbody radiation for quite some time. And this kind of spectrum was, experimentally speaking, well known. That you had that, so you have a spectrum that has a local maximum. So if you go to a very long wavelength, and then the intensity there is gets smaller and smaller. But also, when you go to shorter wavelength, the intensity also gets smaller eventually. And there were theorists that were trying to explain this, because this is the picture you have towards the end of the 19th century. You have a complete description of electricity and magnetism in the form of Maxwell's equations. People understand now that light is electromagnetic radiation. And you have development of thermodynamics based on kinetic theory of molecules. So, and you have atomic theory that's developing. So people understand that when you look at an object like this, it's made up of charged particles, electrons, and that when it gets hot, that there are electrons oscillating around. That has a lot of kinetic energy. So they understand, they can get a kind, so this is the kind of thing that they couldn't have imagined describing in Newton's time. Because, in Newton's time, they look at this ball, they have no idea what it's made of. By the end of 19th century, it's within their grasp. They can say, oh, it's made of charged particles. As they get hotter, they oscillate. As they oscillate, they emit electromagnetic radiation. So they feel like they can actually develop a theory to describe this theoretically, not just experimentally. And that's where they ran into problem. Now, I want to see if Does this let me show Rayleigh-Jeans prediction? I don't think it lets me show Rayleigh-Jeans prediction. So I guess I'll just have to draw it. Let me just draw it. So I'm not going to do the actual derivation, mainly because I can't. But I'm also not going to do it because it's another description of a theory that turned out to be wrong. So, well, I mean, it's a theory you know now, but so this is a prediction of something called Rayleigh-Jeans. How many here are familiar with the name Lord Rayleigh outside of Rayleigh criterion? It's the same Rayleigh. How many here know? Have you heard of the phenomenon called Rayleigh scattering? No? You guys never asked the question, why is the sky blue? Yeah, the way it's explained is through Rayleigh scattering. As the light comes, the light oscillates the electrons, and that oscillating electron is like an oscillating dipole. It has a frequency dependence. It happens better at shorter wavelengths. So the scattered light has more blue color in it than red. That's why the scattered light looks blue. And near the sunset, when you look at the light that has come through the atmosphere, the light that hasn't scattered looks redder. Right? Like you cover this sometimes in like middle school science classes, right? In these qualitative terms. And in upper division physics, you might actually do the derivation, but I won't. It's the same Rayleigh. So he's known for doing that kind of derivations. So he and, I don't know who Jeans is. So it's called the Rayleigh-Jeans law. It describes a prediction of electromagnetic radiation from a hot object, a blackbody radiation. And here's a part of the prediction they do get correct. They do get correct that as you go to longer wavelengths, the intensity of the radiation would die off, that it would go down. And you can understand this. Do you guys remember seeing that oscillating dipole simulation I showed and how the amplitude of wave changes depending on the frequency? Did I show you that? Maybe not. Okay. Let me quickly do that just so that you have some intuitive feel for it. So, to do it properly, it would take a lot of math. But I can just show you a quick simulation so that at least you have some sense that it's intuitively correct without going through a bunch of complicated math. Radiation. No, I don't know. Maybe. Radiating charge. This is the one. So I can set this charge to go in a circle. That's the one I like the best. Let me make the amplitude kind of small. And so this is sort of the magnitude of the radiated wave. And if I want this to be larger, more intensity, then I could make the amplitude of the oscillation itself larger. Or the other thing I can do is I can increase the frequency. So the electromagnetic radiation is a result of accelerating electric charges. So when it's oscillating more quickly, it has greater acceleration, so it emits more radiation. Intuitively, that makes qualitative sense. That if I have a charge that's oscillating a lot more quickly than another charge, then it would be emitting away more electromagnetic energy. Yes. Yeah, as long as it makes somewhat intuitive sense, like saying 2 is greater than 1, then let me just move on from there and not try to prove how 2 is greater than 1. So Rayleigh-Jeans law. So Rayleigh-Jeans law predicts that portion okay. It says longer wavelength. That means smaller frequency. It says that longer wavelength, yes, less intensity of light emitted. But where Rayleigh-Jeans law fails is when you run the calculation for shorter and shorter wavelength, this is what Rayleigh-Jeans law predicts. You can find this figure in the textbook. Just keeps on going up without limit. There is there's no known physical effect that Rayleigh and Jeans could consider that would force this intensity to come down at the high frequency range or shorter wavelength range. this acquired a term that actually people use even today in different contexts. This is called ultraviolet catastrophe. I mean, you know, catastrophe makes it sound like it's a terrible thing. Well, it's a terrible thing for theorists. It's a terrible thing for the theory. Because what theorists would predict is that if you see the oven here, right? If you open up an oven, what the theory predicts is that you will be blinded by a burst of gamma rays from the oven, or X-rays, or ultraviolet rays, whatever. Now, it doesn't actually happen, so it's not real catastrophe. It's a catastrophe for the theorists who were predicting something that doesn't happen. But so that was quite a puzzle, and a lot of people have worked on it, and it really came down to there is no known law of physics that would lead to this limiting behavior. It really came down to there is no known law of physics that would lead to this limiting behavior. So the solution to that, the solution to this problem, solution to this ultraviolet catastrophe, is proposed by a German physicist named Max Planck. I guess he must have been fairly there. In Germany, there's a bunch of institutions called Max Planck Institute. How many here from Germany? Never mind. So Max Planck is the guy who suggested a solution to this ultraviolet catastrophe. And I want to just present his solution and sort of redrive some of these things that I think we can do from that solution. So let me put it this way. So blackbody radiation, I'm just going to write down ultraviolet catastrophe, which results from Rayleigh's law. I'm writing down all these terms because I'm kind of going through fast and I'm not really doing thorough coverage of this. If you're interested, you can Google search and read, or you can read the textbook. So let me start out with Max Planck's solution to this ultraviolet catastrophe. So let me start out with the result. The result that he derived, you can find it in your book, chapter 6, Blackbody radiation. So read through it, and this is the plot you are seeing. This is describing Wien's displacement law, and Wien's displacement law. Stefan Boltzmann law, whatever. So those are all experimental laws. People were just finding those experimentally because blackbody is common, easy to measure. You can discover all those things experimentally. So where people were running into the problem was, how do you actually understand this? And the Rayleigh-Jeans law, the first attempt at it, failed because it results in ultraviolet catastrophe. So the question was how to handle the short wavelength or high frequency case. And this is the result. This is a Planck law for blackbody radiation. That's what he derived. And in order to derive this, I will write it down on the board. In order to derive this expression, I'm putting this on the board because that's the one expression I don't have memorized. Everything else memorized. So to derive this, Planck had to make an assumption. So this is Planck's assumption. He assumed this way. So when you have this object which is radiating electromagnetic radiation, you can think of it like this containing some hypothetical oscillators. As in, imagine you have, I'm just drawing it schematically. Imagine I have some electron here, which is going to be vibrating back and forth, and as it vibrates, it emits electromagnetic radiation, right? So this is my oscillator. It's kind of a model for this object. And it's a model that's meant to be widely applicable because black bodies are quite common. Our sun is a black body. You are a black body that emits something like a 10 micron wavelength infrared radiation. Yes?
Can we define black body? What is it?
Um,
Formal definition of black body?
Well, technically, black body is an object with an emissivity of 1. That's the perfect black body. But black body, in the sense I use the term, as in something that has some non-zero temperature, so it emits thermal radiation. Everything is a black body. I guess atoms? Okay, I guess a single atom is probably not a black body. But any macroscopic object is a black body. Yeah? So those black bodies are made up of an oscillator. And this is what Planck assumed. He was trying to just come up with a solution where something would limit the amount of energy that can be emitted at the high frequency limit. So he assumed, okay, this oscillator, it can only have energies, in discrete units. And he said this discrete unit of energy, so the whole purpose of introducing this mechanism is to limit the amount of energy at the high end. So you say this discrete unit is, this unit is equal to, it's proportional to frequency. So that's an important part. And at the beginning, what he did was, well, it's proportional to frequency. So let's say here's a constant of proportionality. And this, I guess, I don't know, when he initially started the derivation, unless the myth I heard was that he was hoping this would cancel out of the derivation. Like when you do any kind of classical mechanics with the mass, you have masses in there already, hoping that it'll cancel out when you're dealing with the gravity, right? So, but this constant of proportionality didn't end up canceling out. And this is what is today we call Planck's constant. And it's one of the, what is it? One of three fundamental constants of nature: gravitational constant, speed of light, and Planck's constant. Planck's constant. But so that's the assumption he made. You can think of it like, I like a money analogy. Imagine someone said this. So, you know, whatever money you have in your bank account, let's say you can withdraw it all. And let's say they told you the only denomination you can take is a dollar bill. Can you take the entire amount of money in your bank account? Well, close to almost the whole amount, okay? What if I told you you could only take it in $100 bills? Maybe depending on how much money is in your bank account. Now, what if I told you you can only take it out in the denominations of $1 million bearer bonds? Most of us can't take any money out. So that's what this is. That's what the mechanism here is. As the frequency goes up, the discrete unit of energy this oscillator can have gets limited. So at low frequency limit, this limitation wouldn't amount to anything. So, you know, Planck was looking for, okay, two things. One, agreement with Rayleigh-Jean's law at low frequency. And this kind of accomplishes that because this at low frequencies, this limitation has no effect. It's like somebody forcing you to take your money in dollar bills. Because it's a lot of dollar bills, but you know, you can take all your money that way, close to all of it. But he was looking for at high frequencies to disagree with this, to force the intensity to go down, and this assumption would force that to happen. So it's a bit of an ad hoc assumption. Like if someone were to ask Planck, like, why did you assume this? His only answer would have been, well, it gives me the correct answer. The correct answer being this. And, I guess I can, I don't have a lot of time. Let me demonstrate the correctness of that answer. Let's see, Does it do the plot? Okay, they do a plot. So if you want to plot it, you can plot it on your own, put it into Mathematica. And if you just want to plot something numerical, you can just set HC all equal to 1, KB, T all equal to 1, and just let lambda be whatever. That'll be it. What I want to use our time for is I want to show you that, it says it's a leftist exercise. Let's try it and see if I can actually do it. So this is the intensity as a function of wavelength. This is a result that we are hoping for. So if we take this intensity as a function of wavelength, and here's one of the experimental laws we know. We know Stefan Boltzmann law, and the second one that's in the book is the Vince displacement law. Let's see if so Rayleigh-Jeans law is clearly, it doesn't agree with the Stefan Boltzmann law because it predicts infinite intensity at any temperature. So let's see if Planck's law will give the correct, agree with the, let's see if a prediction of Planck's law will agree with the Stefan Boltzmann law. So what we are hoping is that when you take the intensity, and I'm hoping they gave me the correct expression for doing this, integrate it with respect to wavelength, with wavelength going from 0 to infinity. I'm hoping the result I get is proportional to t to the 4th power. Yeah? Okay, before I start on that, let me make sure I have correct units. For this to work out correctly, so I'm going to need to have, so this is supposed to be equal to this. This is supposed to have unit of intensity, or power per area, or which would be joules per meter squared second. That's the unit I'm supposed to have. So the unit of I as a function of lambda they've given me, it's supposed to be intensity density. So this is supposed to be this whole thing divided by wavelength or meter. So this is supposed to be unit of joules per meter cubed second. Let me make sure that's what they gave me. So, I guess I didn't give you, so Planck's constant, can anyone guess what the unit of Planck's constant should be from all the information you have so far? So this is a discrete unit of energy. So what is the unit on the left-hand side? Joules. So I have frequency here. So what's the unit for Planck's constant? Joule second. So that's a unit for Planck's constant. So I have Planck's constant here. So it's a joule times a second times meter per second squared divided by meter per second to the 5th power. And since these are unitless, I'm going to, well, this is also unitless. So I have meter to the 5th power cancels that. So I get joule divided by meter cubed. Let's see, how does, let me work out the seconds. So second times second to minus 2 divided by second to minus 5. So, sorry, I don't know why. Sorry, thank you. So I don't have that. So, okay, so I have, so all of this combines to just over second. That is the unit I was looking for, right? Okay, so they gave me the correct unit for working this out. And so I wanted to just show you a technique using calculus to actually do a calculation like this. Because this is the instinct that a lot of people would have in seeing an expression like this. And so you are going to integrate this with respect to lambda. Lambda is your variable. This is your variable, and these are the places where you sit. All right, that's fine. I can do that integral. And then you see lambda here. And maybe you think, I don't know how to do that integral. And what I want to show you is this can be done. there's a simple substitution you can do. The technique here is whatever you want to integrate, you want to be able to express it as a unitless, parameterless, numerical quantity. And you can push that off to Mathematica to finish it. Then the rest is what will give you what we are looking for. So that's the technique I want you to demonstrate. Let me do that quickly. It actually won't take that much time. So let me do that. So that's what we are looking for. I already have that there. So let me just copy in that expression and just start chugging away at it. So it's an integral from lambda equals 0 to infinity, that whole thing, 2 pi hc squared over lambda to the 5th power times 1 over e to the hc over lambda kbt minus 1 d lambda. All right, so that's the integral I want to do. So the technique I would use is algebraic substitution. So I want to make this a substitution. I would really like this whole expression to be simply 1 over e to the x minus 1. I feel like then, if this x is just a unitless parameter, then I can just let that be, done by some kind of Mathematica, right? So let me try doing that substitution. So if I want to do that, then I'm trying to set this equal to x. So my x is equal to hc over lambda kbt. All right, I need my d lambda to be able to do the substitution. So take the differential, then dx is equal to, these are all constants, hc over kbt, and I have this lambda, derivative of this minus 1 over lambda squared, right? So minus 1 over lambda squared, and then chain rule, get the lambda back. Good? All right, or let me just solve this for d lambda to make it easier for me. D lambda is equal to minus lambda squared kbt over hc dx. Good. All right, let's do that substitution. I guess there's one more expression that's useful to have. I should have this solved for lambda also, because I'm going to need to use that to get rid of this lambda outside. So say lambda is equal to hc over x kbt. All right, let me do that substitution. It's kind of tedious, but not difficult. So this, I don't need the units anymore. This whole thing is equal to, limits of integration. So when lambda is equal to 0, what is my x equal to? Infinity, right? Or as lambda approaches 0, x approaches infinity. So let me let x go from infinity. What about when lambda approaches infinity? X approaches 0, so it goes from infinity to 0. And I'm actually happy to see that because I gained this minus sign in the substitution, and it'll just flip this back the way I kind of want it to be. All right, so let's keep going. 2 pi hc squared. I think I'm going to convert 3 of these factors. Wait, 3? Wait, let me. Yeah, I'm going to convert 3 of these factors and leave 2 behind to be canceled out by this. Good. So divided by 3 of these, or hc over xkbt raised to 3rd power. I still have 1 over lambda squared. I'll clean this up later. That's equal to 1 over e to the x minus 1 Now d lambda, I need to plug this in. Minus lambda squared kBt over hc dx. Good. Let me do the cancellations that I was hoping for. Lambda squared cancels. And I've successfully gotten rid of all the variables except for x. The rest are all constant parameters. So let me do a bit of a cleanup here. Let me clean up this expression first. So it's going to be 2 pi hc squared over h squared c, h to the third, c to the third, h third, c to the third. And then all of this goes on the numerator. So x to the third, kb, k third, t third. All right. Times 1, that. And these constant factors, minus kBt over hc. So I want to just combine all the factors so that I don't have a bunch running around. So I have kBt to the 4th power. That's what I end up with. This h cancels that. So h to the 3rd power. That cancels that. That cancels c to the 2nd power. I got all the constant factors correct? All right, so let me rewrite this integral this way. I'm going to flip the limit and let that take care of the minus sign here. So what this integral ends up being is factor all this out of the integral. 2 pi kb to the 4th power divided by h to the 3rd power times c to the 2nd power. There's a reason I'm writing it this way. I wrote all the constant coefficients except for t. So now I can write t to the 4th power. Let me write down the integral that I left behind. This is multiplied to the integral with respect to dx, with x going from 0 to infinity, x to the 3rd power, and 1 over e to the x minus 1. So now if you ask me, do I know how to do this integral? I don't know. I guess I could do it with integration by parts if I had to, but I don't feel like I had to, because I can recognize at this point this integral, whenever it's done, is going to be unitless, parameterless, dimensionless, numerical quantity, which means I can just do, you can actually do this on your calculator. You don't actually need Wolfram alpha for that. Graphing calculators can do this, because all it is you're integrating x to the cube divided by e to the x minus 1 from x equals 0 to x equals infinity. And that'll give you some, I don't know, 6.5. So you can say that, all right, whatever this integral is, this is equal to 6.49. And I have my result. This intensity integrated over all wavelengths is proportional to t to the 4th power. And if everything really works out, this 6.49 times all of this should equal Stefan Boltzmann constant. I guess not enough time to go into photoelectric. Well, yeah, let me do that. I think we've spent enough time on this, so might as well finish it and get the payoff. So let me just take this. Actually, let me take that number times all these other constant coefficients that I didn't actually get rid of. 2 pi times Boltzmann constant to the fourth power divided by Planck's constant to the third power divided by c squared. So I'm expecting something with the unit of joules per meter squared, watt per meter squared per Kelvin to the fourth power. So hope that's what we are going to get. So watts per meter squared, yeah, it is one Stefan Boltzmann constant. Wolfram Alpha is smart enough to know that. Good. So that's it. So that's Planck's law. And what I want to emphasize at this point is that in order to derive this expression, Planck had to assume this. And if somebody asked you, asked Planck, why did you assume this? The only answer he could give was, well, this is why. He doesn't have any a priori reason. This is the contrast to the special relativity. In special relativity, we started out with the postulates of special relativity. We said, all right, these two are self-evident truths, and we'll derive the rest. With the quantum mechanics, at least if you are being historically semi-correct, this is not a self-evident truth. It just happens to lead to the correct result. This is what people call, let me write it down so that you have it. This is what people call ad hoc. It's Latin for, I think, here and there, or it's like as it comes up. It's an ad hoc assumption. And as we introduce quantum mechanics the rest of this week, you will see that's what quantum mechanics is built on. It's built on these foundations of ad hoc assumptions, which are not mathematically very appealing. You know, with the special relativity, you had almost like a search for aesthetics. The Maxwell's equations, they are so beautiful, you want them to be right. So for those to be right, the postulates of special relativity has to be right. With the quantum mechanics, it's going to look ugly because it's going to look like a patchwork of these ad hoc assumptions. Out of those, some pattern will emerge. And in fact, I can start off with one thing. So we said, let's see, how do I put it? So here, this is how I was trying to describe it, right? Planck was imagining these hypothetical oscillators, which he doesn't know very well. So to which he assigns some special property which are not familiar, but which gives the right result. And you know, who's to say what these little microscopic oscillators are like? Who's to say like this isn't really their property? And Einstein is the one to take this idea and actually apply it more broadly. So so we don't have time to go over the whole thing. So this is the base. This is the explanation of something called the photoelectric effect. It's an effect observed when ultraviolet light shines on metal surfaces. They see electrons popping out of the metal surface. I can show you videos and all that next time before your lab, the lecture before the lab. And it had certain features to it that people had a difficulty explaining using classical theory of electrodynamics. And Einstein, actually his Nobel Prize is based on his explanation of this. He didn't get Nobel Prize on special relativity because I guess special relativity was too theoretical. And if you want to get Nobel Prize, you want to do something useful with it. That's why mathematicians don't get Nobel Prize. Well, they get usually Nobel Prize for economics. They get Fields Medal. They have their own prize. And the starting point for Einstein explaining photoelectric effect was this additional assumption. He assumed this. He said, so this is for this is an extension of this idea for photoelectric effect, where there are no thermal oscillators like there are in black bodies. He said, let's see, how do you put it? So when light exchanges energy with when electromagnetic radiation exchanges energy with any other object. So when light interacts with matter, the amount of energy that the light can transfer is limited this way. The amount of energy exchanged can only come in units of this, or it can only be some integer number times HF, where this is integer. I guess at first sight, this looks like the exact same thing as this, right? The amount of energy comes in some discrete quantized quantity. The difference is this. This pertains to some unknown object. No one knows anything about oscillators. Light, people have been debating about light for centuries, since Newton's time. There was this whole debate about corpuscular theory of light and wave theory of light. Wave theory won. We are supposed to believe that light is a wave. But when you start introducing this discrete energy, it begins to sound more particular, like particle. You are almost saying light interacts with matter like a particle. So what Einstein is claiming with this assumption is much more broadly applicable to something that we are supposed to know very well. That's why I guess it's Nobel Prize worthy. Planck stopped here. He stopped with oscillators. He didn't try to extend this assumption to even more. Einstein took that idea and extended it to things that people thought they understood to explain an effect that we're going to go into next Thursday. And if there's time next Thursday, we'll talk about de Broglie hypothesis, where somebody takes this idea and extends it even more, applies it even more generally. The Planck's blackbody radiation law is what actually led to the correct prediction. I put quotation around the prediction because it's not a prediction at all. It's something that everyone knew. Planck law is the one that actually fits to the experimental curve correctly. And for this Planck law, he had to introduce a poorly justified assumption. The only justification he had for this assumption was that it gave him the correct result. Really, he had no other justification. And this is the thing that I want you to take away from blackbody radiation. This is the most important thing. Planck's assumption that energy of oscillators. So you treat blackbody. So this is the thing that you saw that was really hot on Tuesday. You treat blackbody as being made up of charged oscillators that can take some amount of energy. You say that this amount of energy that can be in the oscillators, energy of oscillators, come in units of some constant that we now call Planck's constant times frequency. So if it's coming in units of this, the only coefficient that can go here is an integer. So this is an integer. And this is what we call now Planck's constant. And it's a very small number that has unit of joule times a second. In your lab manual, there's a value there. For some reason, I can never memorize this number. But it's a very small number. Yeah, I don't think I have electron charge memorized, 1.6 times 10 to the minus 19 coulomb, but somehow I can never memorize this number. But anyways, but this is the main takeaway, that Planck had to assume this to get this correct result that we saw. And what we are going to see today is that, I don't know what the right way to say this was. So Planck was restricting this assumption to these mysterious oscillators, mysterious blackbodies. And it turns out he was not being bold enough. So when you first look at this, it's an assumption, like where's your justification? Turns out Planck was just being way too careful, because it turns out this relationship applies much more broadly. So the first thing we want to look at is something called the photoelectric effect, and I thought I would start out with a video because it's easier to kind of see the demonstration that way. Your lab today is, by the way, photoelectric effect, so you'll be doing actual concrete measurements based on that effect. But there's I found this while I was searching for physics 10 material, and it's actually
we use this natural light instead of the carbon arc we had inside, and we could use this simple electroscope instead of all that elaborate equipment that we had inside. Bill has put a glass plate on the front of it to protect the needle from the wind, and he's wrapped the glass plate with wires to shield the needle from any electric charge that might be on the plate. The wires are connected to the can of the electroscope. And now will you put a negative charge on the electroscope with that plastic rod that gives a negative charge? Here is a piece of lead foil, and if you'd hand me some of the steel wool, I'll get it clean. We'll put it on the electroscope, and of course when I touch the electroscope that discharges it. If you give me the piece of glass and charge it negatively, I'll hold this glass in front of the lead, and there we have a charge. Now I remove the glass, and we see that the electroscope isn't discharging. Now I'll try magnesium. This has to have its oxide removed too, and I'll bend it and put it on here. And now if you charge that negatively, we'll see that it isn't discharging with the glass in place, but if we take the glass away and let the sun fall on it, discharges, put the glass back, we slow the discharge up and take it away, and it discharges much more rapidly. Let's do the experiment once more, this time with the electroscope charged positively with a different plastic that gives a positive charge when it's rubbed. And now when I take the glass out, the electroscope doesn't discharge with the magnesium plate on it as it did before.
So that's the demonstration. As you can see, it's actually a pretty simple experiment you can imagine doing. Now, in your setup, they are kind of all hidden inside the black boxes, so it makes it harder for you to see that. But what the measurements you'll be making of currents, which you have to kind of trust to your control box, is that's coming from this effect. So the first time people noticed that photoelectric effect was, I think, late 19th century. So when people were working the light, they noticed this effect. As you can see, it's a pretty simple experiment. Once you kind of notice the weird thing, then people can do it. So, and it's almost tantalizing because you feel like you should be able to explain it. Let me just sketch what photoelectric effect involves. So in photoelectric effect, what you are seeing, or how you would explain what you see, like what you saw in the video, is you would say, okay, I have some metal surface on which some light is shining on. So you have light shining on it, and what you are observing, or how you explain what you are observing, is that as light shines on it, some electrons pop out, or you get, I guess something like cathode ray. You see electrons popping out of the surface as light shines on it. Now, just imagine you are someone, a physicist working in the late 19th century. So this is after development of Maxwell's theory of electromagnetism, and so you know about electromagnetic waves. And this is when a guy named J.J. Thomson have discovered the electron. I think he discovered in like 1890 something. So electron is known as a particle. People have been working the cathode ray tubes. So how would you explain what you are seeing here? Where would your first starting place be? Like, why would light interact with this charged particle in the first place? Is there something about light that you would say, oh, that should interact with the charged particle? Yeah, light is made up of electric and magnetic field. So what we describe as light, it's an oscillation of electric field and magnetic field. So, I could describe light kind of this way. It would look something like, wave of, or I was told to avoid saying wave because some people don't. So you have this these arrows are representing electric field. And as light comes, this is oscillating back and forth. So if you have a charged particle sitting here, then as this electric field is oscillating, so on the very surface you have this electric field that's oscillating back and forth. That's going to cause this charge to feel a force due to this oscillating electric field. It's going to be shaken. You can imagine that this charge will, maybe as it's being shaken, it might gain enough energy to leave this surface. Right? So that's what I mean. It's so tantalizingly close that you feel like you have almost all the pieces you need for explaining this phenomenon, except that there were a couple odd things that you just couldn't explain. Let me just, so this is, I guess I can start out with what you saw in the video. So you can list 2 or 3 different things. The biggest thing comes down to this. Let me not use red. This effect, this entire phenomenon is frequency dependent. Now, I don't know, does it make sense that it should be frequency dependent? So by frequency dependent, I mean, so this, electromagnetic wave of light, if we made it higher frequency, shorter wavelength, then this would be, this oscillation would be happening at much greater frequency. Like it'll be flipping back and forth at, double the rate it would in the red color when it's in the ultraviolet light. Then just intuitively, like if you have electric field that's flipping back and forth more quickly, then does it feel like maybe this should gain more energy? Maybe, yeah. I mean, so it depends on your intuition. If you feel like, as it's flipping back and forth more quickly, then maybe this should shake more violently. Maybe. Now, so here's the part that you really cannot explain. How do I explain it? It's what you saw in the video. So you saw with the visible light, absolutely nothing happening. And the visible light, it was pretty bright. And what I'll tell you now is that it didn't matter if you made that 60 watt light bulb, if you replaced it with a 600 watt light bulb. So let me qualify this carefully. So it's below threshold frequency, it's intensity independent. By independent, I mean, it doesn't matter how much intensity you have. If you're below a threshold frequency of light, then nothing happens. Now, this is the part that you just can never explain with the wave model of light, because what does the intensity of light relate to as far as its electromagnetic property goes?
The square of
so the magnitude of electric field, right? If you increase the intensity, you are increasing the, increasing this magnitude of the electric field. So, if you have a charge here, and if you apply large enough electric field, could you apply enough force to make it pop out? And when you do the analysis in classical mechanics, like you should be able to. Even if you were to look at what is the rate of change of electric field, well, you can keep the frequency the same. So as far as the rate of change of electric field goes, whether you double the frequency or you double the electric field or quadruple the intensity, they should work out the same thing because it's the same sinusoidal thing. You can make this slope steeper by either increasing the frequency, so decreasing the wavelength, or you can do it by increasing the amplitude. So this is really the biggest piece that you can't explain based on classical mechanics, or you cannot base. So this cannot be explained by thinking of light as electromagnetic. By thinking of light as electromagnetic wave, because if that's all the model of light you have, then it's a very puzzling thing that once you fall below certain frequency, that no matter how strong an electric field you apply, that the photoelectric effect won't happen. And on the flip side, if you have enough frequency, so as you reduce the intensity, what you would see is that you would see that the rate of discharge is slower as you reduce the intensity. But what you would see is that no matter how small the intensity, you would always get some discharge. So that's another thing that's kind of hard to explain. Like, if you reduce intensity enough, then are you just simply not shaking the electron enough that it would pop out? So I will say this puzzled people long enough, decades. So Einstein got his Nobel Prize 1921. I think I had to look it up while I was. They had some errors in the UC Berkeley physics lab, so historical errors. Physicists are not good historians, so I had to fix that. When did they say it last? I don't know, 1890 something. So for more than a decade, some people were studying it, and they didn't really have a good explanation. And well, chronologically, this comes first. So I guess, once again, physicists are not good historians. I don't know where Einstein got his inspiration, but it's oddly similar to this. So what Einstein hypothesized was, well, maybe when this electromagnetic wave interacts with particles, maybe there's some kind of minimum amount of energy that has to be transferred. So call that minimum change in energy. And this minimum amount of energy that has to be transferred is equal to Planck's constant, which comes from here, times the frequency of electromagnetic wave. So it's oddly similar to this, because if you're saying, let's see, so it's oddly similar to this. The difference being that here we were talking about the frequency of the oscillators. So these hypothetical oscillators, they are not even real objects because it's a way of modeling a black body. So it's something that's poorly understood. But electromagnetic wave is supposed to be something that's very well understood. There's a whole set of 4 differential equations that tell you exactly how it behaves. But Einstein was making this bold assumption that you could somehow generalize from this and say, well, even for this very well understood thing of electromagnetic wave, that this might be true. And in fact, I think he's saying a little bit more than this. So each time electromagnetic wave exchanges energy with the electron, so it's not enough to say that amount of energy exchanged is simply integer multiple of this, because if that was the case, this could get enough energy when you have low frequency of light. So really this is where you cannot avoid introducing this idea that light is a particle. That when you think of interaction of light with the matter, you have to almost look at it like a collision between two particles. So light is a stream of particles of a certain energy that's colliding with this electron. And if that stream of particles, each individual particle has enough energy to pop out an electron in a single collision with a high enough frequency, then it would. But if in a single collision it couldn't pop it out, then before there's a chance for next collision, this electron would lose energy again. So this is where, like, if you are trying to avoid saying the word that light is a particle, you twist yourself into whatever jumble. So you end up having to say you are dealing with energy of a photon, which is the name we have given to this light particle. And energy of photon is Planck's constant times frequency of, well, I guess we are still treating it somehow like a wave, because like, it wouldn't make sense to talk about frequency unless we are still dealing with the electromagnetic wave, right? Like, suppose I asked you this. What is the frequency of this still ball? Is that a valid question even? Not really, right? If you're talking about it as oscillator, it has some thermal frequency, then that's one thing. But if I'm telling you, treat this like a point particle. It doesn't have any constituent parts, and what is its frequency? Particle doesn't have a frequency. Particle has a velocities, momentum, those particle properties. Waves have frequencies. So in this expression, you are containing those two seemingly self-contradictory quantities. So we are treating this light now like a particle, but at the same time we are doing that, we are not getting rid of any of its previous wave properties. We are still treating it like a wave. So this is the bold assumption that Einstein made, and he turned out to be right. There's a guy, so one of the things you can do is you can then not treat this like a collision between a particle and another particle. So you could say, you could say things like, so this is what your lab is about. You could say things like the maximum kinetic energy of the electrons that are popping out. Well, that must come from the energy of the photon. So that would be, Planck's constant times frequency of light. But, well, this electron is somehow bound to the surface. Under normal circumstances, it doesn't just spill out of the metal. So there must be some kind of potential energy, negative potential energy binding it. So you say, all right, so this is how much energy you are adding each time with each collision, minus whatever potential energy that you need to overcome first. And this is what's called work function in your lab. So this is a pretty simple, like a simple sort of analysis of what must happen based on collision of two things that have energy or can have energy. And once you have electrons that are popping out with some amount of kinetic energy, then you can think of some electrical arrangement to try to measure this. That's what your lab setup is. But this is a pretty simple prediction, and that you would have, I guess this is the prediction, that maximum kinetic energy of the particle popping out would be linearly dependent on the frequency, down to the threshold frequency, where you would have, I guess, zero maximum kinetic energy, that would be h times the threshold frequency. So this would be a way of figuring out what the work function is. So that's Einstein's theoretical prediction, surprisingly simple. Well, maybe because it's simple, somebody did do the experiment like a few years after Einstein proposed it, and like a couple years after, I think the experiment was done in 1916. And once you have a theory that's experimentally verified, now the Nobel Committee can actually give him the Nobel Prize that they knew had to give to Einstein at some point because he's a genius or something. So this is a photoelectric effect. Once you get over this hurdle of hearing that light is actually a particle, then it's actually mathematically pretty simple. Right? Everyone here okay with the idea that light is a particle? Yeah?
Is it the particle that's causing the wave, or do they both get emitted simultaneously?
Well, think about electromagnetic wave. So let's see. If you have, electromagnetic wave like this, I think I see what you're saying. So when we talk about sound waves are actually made up of particles. It's made up of air molecules. But the air molecules themselves are not the sound wave. Air molecules simply make up the medium that the sound waves travel in. Now, what is the medium for this light wave? What did it say the medium for the light wave was?
Ether.
Well, we went over for 2 weeks how it doesn't exist. So what is the medium for the light wave?
Electromagnetic spectrum.
I mean, so what we call light wave is an oscillation of electric field and magnetic field. So, or it's a propagating oscillation of electric field and magnetic field. I can get electric field to oscillate by just taking a charged particle and shaking it, right? So this is the question. For this shaking of the electric field to propagate through space, does it need to depend on some kind of material medium? No, right? It can travel through vacuum. So light has no medium. Unlike sound does need this air to travel through. If you vacuumed out all the air in the room, you wouldn't hear me. Well, aside from dying soon. So you are asking, okay, so then is it a particle that's making up the wave? Well, there's nothing material underneath the electromagnetic wave to consider as a particle. So that's the does that answer at least some part of your question?
I'm just wondering if it's like the photon is somehow charged and that's what's creating something around it, or is it just like they're both?
I can tell you one thing. Photon has no charge. Yeah. So if you have a charged particle, something that's negatively charged, as I shake it, it's going to generate electromagnetic wave. But the electromagnetic wave itself, it doesn't have any charge. And you kind of know that because the one light wave doesn't actually interact with another light wave. If I cross these two in the middle, like they don't interact with each other. And in fact, this is why we get the whole superposition principle and all that stuff, because one oscillation of electric field doesn't interact with another oscillation of electric field. So I can tell you right now that this electromagnetic wave, it's not associated with anything that has an electric charge. So with the quantum mechanics, I will say this much. If as you hear the words I speak, if you thought, oh, that makes sense, then I will just warn you that you may not have thought it through too much, which is okay maybe for this class because it's lower division physics. But Feynman said these famous words. Richard Feynman, he did a quantum electrodynamics, whatever. That if you think you understood the quantum mechanics, then you haven't understood it, or something like that. At some point, maybe not today, but as you are going through quantum mechanics, some aspect of it should cause you to puzzle. And I will tell you, with the special relativity, I said there is no such thing as paradox in special relativity, because it's just misunderstanding. With the quantum mechanics, there are paradoxes. There are unresolved questions, not of things that you can resolve by experiment, but more of what we call interpretation of quantum mechanics. So let me just leave you with this. 9 formalisms of quantum mechanics. I think that's the name of a paper. 9 formulations of quantum mechanics. So I think I did say at some point, quantum mechanics has a traumatic childhood, right? And this is one aspect of it. There aren't 9 formulations of special relativity. But with the quantum mechanics, there are many different ways of expressing it because it's just there are aspects of it that just deeply disagree with our classical intuition, and there's no easy way to simply explain it. Here, use this Lorentz transformation, and everything will be fine. There's nothing like that for quantum mechanics. So what I want to do starting today is to introduce you to some of the quantum mechanical assumptions, quantum mechanical things that, I introduced this by saying this was an ad hoc assumption. And things are going to get less ad hoc. We are going to have more fundamental assumptions, things that's universally applicable. But it'll still be an assumption. It's not something you can derive from classical mechanics. It's something new that you have to be told. So I just want to set up the picture and describe what's seen experimentally as a kind of one of the early confirmation of the particle nature of light. So this is the setup for a Compton scattering experiment. This is what it looks like. So in something called Compton scattering, it's a scattering of electromagnetic radiation by a charged particle. So in some sense, I mentioned the Rayleigh scattering, right? Yeah, so it's similar to Rayleigh scattering, except at the limit where the energy of the photon is much, much higher than Rayleigh scattering. So you have an electron sitting somewhere, and you have, for whatever reason, people use the letter gamma to indicate photon. So you have photon come in, strike the electron, and let's do a simplistic case. Let's say it's a head-on collision. So after colliding, photon scatters straight backward, and electron goes straight forward. Then electron will be moving that way with some velocity, and the photon will be coming back with some energy. Now, if you hear this description, and I tell you the photon has some incident energy, and as it bounces back, it has some final energy. What does your intuition say about how these two energies should relate? Should they be the same energy? They should be different, right? Why? Why different?
Some energy goes to the electron.
Yeah, conservation of energy. This is a collision. It feels like energy should be conserved. If the electron is moving, so there's some kinetic energy, then you feel like, all right, so the photon loses some energy, right? And you can actually analyze this picture that way with the special relativity taken into account, and you will get the correct result that you see experimentally. And this is why I'm saying this is one of the early proofs that this particle picture of light is correct, is because imagine you are analyzing this instead, trying to treat this photon like a wave. So then what should represent this photon as is some kind of oscillation of electric field and electric field, some kind of oscillation of electric field, right? Now, you can still understand why it would scatter, why you would have electric field coming backward. You would think of it, all right, this electric field oscillating, it meets this electron, it causes the electron to oscillate up and down with it. And this oscillating electron would re-radiate some of the electromagnetic wave backward this way, right? So you say, all right, so I have some of this electromagnetic wave radiation going this way, which is also oscillating. Now, how would you say the frequency of the incident light relates to the frequency of the outgoing light? Same frequency or different frequency? Yeah, your intuition says same frequency, right? And that intuitive answer turns out to be wrong here. Because when people do the experiment, it's usually with X-rays or gamma rays. Shine it, have it collide with the electron, and measure the energy of the light that's coming back, or the frequency, wavelength of the light coming back. Usually wavelength of the light coming back. The wavelength changes in the collision. So the classical prediction is that frequency shouldn't change, so the wavelength shouldn't change. the particle prediction is that, well, energy should change. And what to measure this, the energy does change. And so we'll do the full derivation next Tuesday. It involves actual special relativity. As a matter of personal note, this was the first experiment that I did personally in upper division undergraduate lab at Berkeley. It's a gamma ray scattering experiment where you actually had to take into account the special relativity. Because those gamma rays have enough energy, these electrons are moving relativistically, that unless you use relativistically correct formulas, the results come out wrong. So you can actually see the effect of relativity even in undergraduate lab in a setup like this. So, okay, that's all we have time for. So you have your lab, all the labs are set up.
So we continue with the derivation of the Compton scattering formula. For this derivation, I'm going to follow the approach I've taken in my particle physics note, which I've shared in the context of the class. So let me read through this relatively short section of the note, filling in some of the gaps in the derivation as I go through. So let me start from the top. Compton scattering. The second example I have for you is called Compton scattering, where an X-ray or gamma ray photon scatters from a free electron. So it is an elastic collision process with a simple reaction equation. Photon plus electron becomes photon plus electron. We consider the picture where the electron is at rest initially. A gamma ray photon collides head-on with the electron. Gamma ray photon bounces straight backward from the electron, and the electron scatters forward. This is the case when maximum energy and momentum is given to the electron. With a grazing collision, the electron will have less kinetic energy. So, from conservation of energy and momentum, we have initial photon for momentum plus initial electron for momentum being equal to final photon for momentum plus final electron for momentum. And this time, we do not square these four vectors. This is a counterexample for usefulness of Lorentz scalar. Because we are looking at and calculating everything in the lab frame, we are not using any other reference frame. It turns out straightforward calculation using conservation of energy and momentum components is simpler in this case. So the following are the four momentum components. I have column vectors written for each of the four momenta above, with the electrons starting off from rest initially, and then after collision gaining momentum of P sub e. And I express the photon for momentum in terms of its three momentum, because we will eventually want to derive a Compton scattering formula in terms of the photon wavelength. Setting them equal component by component, we have two equations. And at this point, let me switch over to OneNote so that I can annotate as we go through this derivation. So we have two equations, the energy component of the four momentum, let me call this equation 1, and the momentum component of the four momentum, let me call that equation 2. And we will be needing one more equation, so we have the equation that relates electron energy to electron momentum. Let me call that equation 3. We have three equations and three unknowns: the final momentum of the outgoing photon, final energy of the electron, and the final momentum of the electron. So this should be solvable. It's a matter of going through careful algebra. We will solve for final momentum of the photon, eliminating the final energy and momentum of the electron. First, we solve the second equation for final electron momentum. You do that by moving the photon momentum term over, giving you final electron momentum is equal to the sum of the magnitude of the initial photon momentum and the final photon momentum. That's this equation here. And we square it to get the next equation. The left-hand side is clear enough. The right-hand side is expansion of this product. the initial photon momentum magnitude plus the final photon momentum magnitude multiplied to itself. The product of the first two terms give you p gamma I squared. And we have the cross terms, where p gamma I multiplies to the p gamma final, and their same product from the other cross term, p gamma 5 times p gamma initial, because the order of the product doesn't matter. That's the second term. And the last term is again the p gamma 5 multiplied to itself. Now we can use the third equation, equation 3, to eliminate the momentum of electron from our system of equations. So from equation 3, we can solve it for Pe squared, giving the appropriate factor of C to the energy term on the other side, and moving the mass term over with the appropriate factor of C. Let me call this 3 prime, and plugging this expression for electron momentum into the left-hand side of the equation above, we get this new left-hand side in terms of the electron energy and the electron mass. Now we have eliminated one of the 3 unknowns. In order to eliminate the electron energy from our equations, we take the first equation, which we haven't used so far. So we can solve equation 1 for electron energy squared and plug it in into the equation we have here. So putting the electron energy term by itself with the appropriate power of C, we have electron energy divided by C is equal to initial photon momentum minus the magnitude of the final photon momentum plus MEC. We square both sides, so the left-hand side becomes the expression that we'll plug in to eliminate the electron energy. And squaring the right-hand side, since it has 3 terms, let me expand it out by hand. I have the same collection of 3 terms twice. And let me first take care of the product of each term with itself. That gives me P gamma initial squared plus P gamma final squared plus MEC, the whole thing squared. And now I have to take care of the cross terms. I'm going to highlight each pair only once, but each of the pairs I highlight happens twice. So I have P gamma initial multiplying with the P gamma final, P gamma initial multiplying with MEC, and P gamma final multiplying with MEC. So with those 3 pairs, again there are 2 of each, I have minus 2 P gamma initial times P gamma final plus 2 P gamma initial times MEC minus 2 times P gamma final times MEC. This is the equation that's in the note. Left-hand side equals the final right-hand side. Now we plug this into the first term of this equation here, using the space below. P gamma initial squared plus P gamma final squared plus MEC, the whole thing squared, minus 2P gamma initial times P gamma final plus 2P gamma initial times MEC minus 2P gamma final times MEC. That's just the electron energy over C squared. Now we have, let me do it in different color, minus MEC squared. That's the left-hand side. All of that is equal to the right-hand side, P gamma initial squared plus 2 times P gamma initial times P gamma final plus P gamma final squared. You can see some quantities cancel right away. The electron mass terms here on the left-hand side cancels out, opposite signs, same quantity. And fortunately, we are able to cancel out some squared terms, p gamma initial squared and the p gamma final squared. The remaining terms are what we have in the notes. These 1, 2, 3 terms, and the one remaining term on the right-hand side. We collect like terms, by which we mean moving the initial photon momentum times the final photon momentum term to the right-hand side, where there's another term like it. Then we have coefficient of 2 in front of a term, minus 2 in front of a term, and this will become 4. So dividing through by 2, we get this simplified expression here. And this is a curious thing. I see this kind of arrangement often. In fact, we've seen something like this in the derivation of the thin lens equation in optics. We have 3 terms, which are formed by product of 3 possible pairings of 3 variables. The initial photon momentum, electron mass, and the final photon momentum. When you have something like this, it becomes a lot simpler if you divide it by product of all 3 variables. Because then instead of having product of 2 things on the numerator, you just have the one thing that didn't get cancelled out on the denominator. So for the first term, it's the gamma final term that's not cancelled out, so that remains on the denominator after we divide it through. In the second term, it's the p gamma initial that's not cancelled out, so that's what remains on the denominator. In the last term, it's the electron mass term that's not cancelled out, so that's what remains in the denominator. And there's 2 on the numerator still. Now we just need one more step to get to the formula that's in the textbook for Compton scattering. This step relates the photon momentum to its wavelength, and we can do it this way. So what we have learned in Einstein's explanation of photoelectric effect is that the photon energy can be related to its frequency by Planck's constant. Planck's constant times the photon frequency, or the EM wave frequency. And because a photon is a massless particle, its relationship between energy and momentum is simply its momentum times speed of light is its energy. We actually used that above when we wrote the 4 momentum for photon in terms of its momentum. Now, on the right-hand side, we can use this relationship for waves, that wave speed is equal to wavelength times the frequency. So, solving this for f and plugging it in here, we get the right-hand side that's equal to Planck's constant times speed of light divided by wavelength, which means the speed of light cancelling out, photon momentum is Planck constant divided by its wavelength. So if we number this equation, equation number 4, we can plug this into equation number 4 to get final photon wavelength divided by h, it's the reciprocal, minus the initial photon wavelength divided by h is equal to the same right-hand side, 2 over MEC. And we usually multiply this through by h to make the left-hand side simpler. And that's the result that's derived in the note. This is the Compton scattering formula in 1 dimension, and it's the result you'd get from the textbook formula if you plug in theta is equal to 180 degrees. This theta is the angle between the instant and the outgoing photon, and this corresponds to the head-on collision. Let me continue reading. A few things are worth noting. Despite its simple appearance, no gamma factors for 1, this expression is relativistically correct. We started with the conservation of 4 momentum and used only relativistic formulas at every step of the way. This is fortunate because we find that for many gamma ray photons, with the energies of a few mega electron volts, the electron does acquire relativistic velocities. So only relativistically correct formula would describe the process well. Also, this defines what is called Compton wavelength of a particle. Compton wavelength of an electron is Planck's constant divided by electron mass times the speed of light. So the heavier the particle, the shorter its Compton wavelength. Lastly, this describes a scattering process where wavelength of the photon changes. How often do you see a blue light reflecting from a mirror only to turn red? There are clear challenges in describing this phenomenon with classical wave description. With a particle description, we didn't have to think twice. And the note says I encourage you to work out the more general Compton scattering formula in 2 dimensions. That includes when the photon does not scatter straight back after a head-on collision but scatters at an angle after a grazing collision. And it gives a hint. For the Compton scattering formula in 2 dimensions, it says you can actually follow the same steps above, just to make sure you write the 3 momentum as vectors. And when we square the momentum conservation equation, you are taking the dot product of the 3 momentum to itself. And we'll be looking out for the dot product of the initial photon momentum to the final photon momentum, which will later be expressed as p gamma I times p gamma final times cosine theta, where theta is the angle between 2 vectors. And we can actually do this with the derivation we have above. Let me scroll up and make the modifications. So these are the changes we'll be making. These 3 components of the momentum, 3 vector, we're going to express them as p gamma I, and this component will be expressing it as p gamma final with the vector notation. Now, as I do that, what I have to be careful is when I see the expression for photon momentum that's actually giving you its energy, I have to leave them alone, not turn them into vectors. So let me go through and make those changes. In the momentum conservation equation, I'm going to turn this into a vector and turn this into a vector, getting rid of the negative sign so that this is the actual vector for the final photon momentum. And the electron momentum is also a vector. Forgot about that here. So that gives electron momentum is the initial photon momentum minus the final photon momentum. So here, when I square the second equation, as I do this square, what I should think of it as is a dot product of this vector to itself. So the left-hand side simply becomes the PE magnitude squared, and with the p gamma I multiplying to itself, I have its magnitude squared, and p gamma phi final the same thing. For the cross terms is where I have to mind the vector notation. So this should be minus 2 p gamma I vector dot product with p gamma final vector. Let me make the same modifications to the next equation here. Okay, let's keep going. Now, in this equation, I have to be careful. This was the energy equation, meaning these are not vectors. So I don't do the same thing that I did up there with especially these products. It's just product of scalars. There's no vector involved here. So I leave this equation alone again because it was the energy equation. Anything that looks like momentum is just momentum magnitude. And as we plug this energy equation into that equation, I have to remember there are vector quantities on the right-hand side. So let me make those modifications. The left-hand side quantities, they are all scalars, leave them alone. And here, this should be minus 2 p gamma initial dot product to p gamma final. And this is the step where I have to be really careful because I have 2 p gamma initial and p gamma final terms. This one here, it comes from the energy expressions. So I leave it alone. It's not a dot product, it's just product of magnitudes. This term here, there should be now a minus sign, and it should be dot product of initial momentum vector with the final momentum vector. So next step is now a little bit different. Instead of this, the left-hand side is the same, but for clarity, let me just rewrite the whole thing. So the left-hand side, after division by 2, is P gamma initial times MEC minus P gamma final times MEC. And on the right-hand side, where I collect the like terms, I have the energy term moved over, divide by 2. So that's a P gamma initial times P gamma final. And then I have the original right-hand side term. And let me rewrite this with the dot product written out as minus, after division by 2, P gamma initial times P gamma final times cosine theta, where theta is the angle between these two vectors. So I have minus P gamma initial, P gamma final, cosine theta. Factoring out P gamma initial and P gamma final, I have P gamma initial, P gamma final times 1 minus cosine theta. So this used to be 2. And that makes sense. It is 2 when theta is equal to 180 degrees. And in more general case, when theta can be any value, it's 1 minus cosine theta. So making those changes, 1 minus cosine theta, your Compton scattering formula in the general 2D case becomes the final wavelength minus the initial wavelength is equal to 1 over MEC times, instead of 2, 1 minus cosine theta. And this is the Compton scattering formula in the textbook. And I encourage you to try going through this derivation yourself. It's a good practice. It's slightly different from other relativistic dynamics cases we have seen, and I think it's a great algebra exercise.